Okay, let's think about the question of how we get from one orbit to another, in this case from the first orbit to the second. First orbit being at distance r1, circular orbit at distance r1, second orbit, circular orbit at distance r2. Now, let's just say we're in our first orbit, so radius of the orbit is r1, and we're going to get to an orbit at radius r2, somewhat greater than r1. Not going to draw the orbit right now, because what I want to do is just think about what happens if we deliver an impulse, okay, in f delta t. Now, we've already seen that to get from one orbit to another, we have to have positive work done by a non-conservative force. If we're going from an orbit to an orbit at a greater distance, we need a non-conservative force. The question is, how do we get that non-conservative force? Well, if we got a satellite, the only practical way we have to do this at this point is with rocket engines. Solar sails can do something similar, but you got to get out into a weaker gravitational field before they can have a whole lot of success in moving the position of an orbit. Okay, well, anyhow, so we deliver an impulse just by burning our rocket engines for several seconds. Now, that's a very short time compared to the time it takes to do an orbit, so we just have pretty much an instantaneous impulse, f delta t. And that's going to result in a change in velocity. Now, if our velocity, I've got vi here for the initial velocity before the burn, we're going to have a change in velocity, and it's going to be in the direction of our impulse. So that's going to be, let's say here. So we got a delta v, and that delta v is equal to our impulse, which is the change in our momentum divided by our mass. Now, there's a little bit of a complication when we divide by the mass here that we're going to ignore for the moment. In burning the engines, we lose some fuel, so we lose some mass. We're going to assume that change in mass is not very significant, so we're going to make this approximation. If you're actually doing this and trying to get to a precise orbit, you adjust the length of the burn for the fact that the mass is going to decrease, and you figure it all out. If you got a very significant decrease in mass, you're going to have to do some fairly, not really too rigorous. The analysis is going to involve some calculus, but we're not going to worry about that right now. Okay, so what we get then is we get some final velocity. We'll call this Vf. Okay, now we were at this point moving at a velocity that would keep us in a circular orbit, moving at a velocity at which the mv squared over r, over r1 in this case, is equal to the gravitational force exerted by the planet on the mass. Now that's no longer the case. We're moving this way. Now, our impulse was in this direction. Okay, the impulse could have been in this direction, any direction, but we're just going to assume this particular impulse. And this impulse would tend to move us away from our, it would tend to move us out into a greater distance from the planet. Okay, well, what happens now if we're at this point and we now have a velocity in this direction that's not in the direction tangent to the circle. In other words, this is a direction tangent to the circle. Here's a right angle. That's probably not very well drawn. Don't have a very good angle on the board from here. But we have some direction that would be consistent with the circular orbit, and now our velocity is no longer in that direction. And it's no longer a velocity that's going to give us a circular orbit, because our speed has increased so that our kinetic energy is too great for an orbit at distance r1.